Problem set 6 has us come up with what are called the VSEPR or valence shell electron pair repulsion theory shapes for a bunch of small molecules. To do this successfully, we've got to do two things. One of them is know how to count valence electrons. If you've done the electron configurations in the textbook, the homework, lecture, whatever, that should be fairly straightforward. But the thing to remember is that valence electrons are just the s and p electrons in the outermost orbital of whatever the atom is. So if you look at the periodic table, the number of valence electrons will be the column excluding the d's. So we just don't worry about the d's. If I'm in the first column, I have 1 valence electron, second column 2, third column over here in the p block, I'd have 3, etc. So I'm going to have between 1 and 8 electrons for each atom. So if I have a formula, let's just say I have something like nitrate, NO3, I'd need to count up the electrons as 5 on nitrogen, 6 on each of the oxygens, and because this is an anion with an extra electron, there's one more. So we'd have 5 plus 3 times 6 plus 1, which is, I think, 24 electrons there. Okay, and we'll do that as an example later. Okay, separate from that, we need to come up with a shape. And the whole thing about the valence shell electron pair repulsion theory is this idea that groups of electrons, and I really need to be careful, this pair is not quite true, it's really groups. So it should be valence shell electron group repulsion theory, but they never got to that. In any case, the upshot of this is that all of the groups of electrons want to spread out in 3 dimensions as best they can to minimize repulsions, the negative-negative interactions of groups of electrons. So in a simple case, if I have a central atom, I'll just call it X, and I have 2 groups of electrons around it, they're going to want to get 180 degrees apart. If I have 3 groups of electrons, they're going to want to get 120 degrees apart. If I have 4 groups of electrons, common mistake is to think these guys want to get 90 degrees apart. And that is incorrect. On a flat board or a flat computer screen or a flat page paper, 90 degrees might work, but these atoms are in 3 dimensions. And so we have to consider that, and a way we might do that is consider a cube, if I could draw. And what we're talking about is 4 groups of electrons, is we might have one group back here, one group up here, this group here, and this group here, and the central atom is somewhere in the middle. So we really care about what this angle here is. We can do that with a little bit of trigonometry, Pythagorean theorem, and go through and calculate what that is. It actually works out to be 109.47 degrees. A lot of people round that as 109.5. Okay, so that is the tetrahedral angle, and we have 4 items here. Okay, second to that is, this would be an electron geometry. So we might talk about 3 groups of electrons giving us this 120 degree angle. And then further, we would then start considering whether we have atoms instead of just unpaired electrons. And that's the difference between electronic geometry and a molecular geometry, and I'll focus on that a little bit more. Back to the names of shapes, this first one here is called linear. When I have, kind of cluttered here, 3 of them, I call that trigonal planar. It's a G there. And when I have this 109 degree angle, I think I said it, but the name is tetrahedral. So those are our backbone shapes that everything else comes from. Linear, trigonal planar, and tetrahedral. We can have other things that fall out of this depending on whether the electron groups have an atom on them, because when we talk about molecular shape, we care where the atoms are more than where the electrons are. All right, so expanding on the structures for the backbones of the molecules we have to worry about. We want to make a distinction between the electronic geometry, which is just what VSEPR dictates. It's the electron groups trying to get as far from each other as they can with no regard for whether those electron groups are binding atoms or they're just non-bonding pairs. And I think by example, as we draw some out, maybe that'll be clearer. All right, so we have the electronic geometry where the electrons are, and then we have the molecular geometry, which is what we actually see. We see the molecule has two hydrogen atoms in positions that are relative to the oxygen atom. And we don't see the electrons anymore, we just see the atoms. The electrons, we see the atoms. The atoms are where they are because of the influence of electrons, but we're talking now just about where the atoms are relative to each other. All right, so our backbones for electron geometries, if we have two pairs, it's linear. If we have three pairs or groups, it's trigonal planar. And if we have four groups, it's this tetrahedral. With the second diagram I have here, we have a convention where we show three-dimensional shape by having a triangle, meaning something is coming out of the page, either a pair of electrons or an atom, and we have this dashed line showing the opposite, that something is behind the page. And so that's supposed to tell us it's kind of a three-dimensional thing. And again, here we can start to see, hey, that really is 109 degrees, whereas over here it sort of looks like 90 still. Okay, now we're going to take those backbones and we're going to put atoms on them. So in my linear shape, if I get rid of those dots for electrons and I show that I've bound atoms, I'll call A for atoms, I get a linear molecule here. So a classic example is carbon dioxide. And again, all the lines and dots will deal as a specific example. But what I have here, oops, I just crossed it out. I have a linear relationship. The oxygen, the carbon, and the other oxygen are 3 points make a line. There's my linear nature of things. If I look at the trigonal planar case, I have two possibilities. I can have two atoms and one lone pair of electrons, or I can have three atoms and no lone pairs. So all of the bonding pairs are used up. And they're going to have different shapes. The electronic geometry is the same, but they're different molecules over here. So here's an example of having two atoms around a central atom. This one, actually, all atoms are the same thing, but it's ozone. So my central atom is bound to two other oxygens, and it has this pair of electrons sticking up there influencing the shape. And you can sort of picture that. This top pair of electrons pushes the oxygen atoms down. The name of this shape is the very fancy bent. Okay, if I have three atoms, it's going to look just like my archetypical trigonal planar, and that's what it's called, trigonal planar. An example of that would be BF3, so I could just have boron in the middle, fluorine as the three atoms there. If I go to tetrahedral, I have yet another possibility. So I can have two atoms, so this would have two atoms and two lone pairs of electrons. Those lone pairs of electrons are squeezing the atoms closer together, and so we end up with something like water. And this has that same name we saw up here, bent. This angle is close to 120 degrees. This angle is close to 109 degrees. Okay. If instead of two atoms, we have three atoms, we have the same influences. This pair of electron is pushing these atoms out of the plane, kind of an inverted umbrella, if you will. And the name of this shape is trigonal pyramidal. So we have trigonal planar up here. We have trigonal pyramidal down here, meaning that the atom is going to be a pyramid. Classic example of that is ammonia. I have three hydrogens, like the legs of a stool, the nitrogen with its lone pair of electrons above it. And I kind of squeeze things here, but my last case would be if I have four atoms around that central atom. Those four atoms will be separated by an angle of 109.47 degrees. And classic example of that is this compound CH4, which is called methane. So all the atoms are the same, they're pushed apart. Okay, so those are the shapes we're going to look for. Now we'll go through and look at a couple of examples from the worksheet and go through the process of how we know how many groups of electrons there are. All right, so let's look at an example, OF2. First thing to do is find the number of the valence electrons. So Oxygen will have an electron configuration of 1s2, 2s2, 2p4. And what we care about is the electrons in the outermost shell. So there's my 6 electrons. So I have 6 for oxygen. Each of the fluorines will have 7. And so I end then with 20 electrons. All right, so that's the important first step, how many electrons. Then I do some sort of a skeletal structure. And I might not know exactly what happens, but nature likes symmetry, so most likely I have oxygen in the center and the fluorines outside of it. Okay, at this point, I have shown the atoms, and I have these bonding pairs kind of being used up already. So these electrons, 2 here and 2 here, are 4 of these 20. So at this point I might just say, well, I had 20 electrons, I've taken away 4 for bonding, I have 16 left to spread around the atom. And at this point I just say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So if I were to count this all up, I should have 20 electrons. 2, 4, 6, 8, 10, 12, start over. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. There's my 20 electrons. Okay, now I want to take this, and from this Lewis structure, come up with the name of the shape. There's sometimes I might have to move some electrons around. I didn't get into that, did I? We need to look and see that the octet is satisfied. So this guy sees 8 electrons. This oxygen also sees 8 electrons. And I won't draw it because I'll get cluttered here, but the fluorine sees 8 as well. So this oxygen has its pair here that are completely its, but it also is sharing this pair and this pair. So the fluorine, or rather this pair of electrons, is counted towards fluorine's 8 and oxygen's 8. That's what covalent is about. Co is the sharing part of the electrons. Okay, so again, back to that, that structure that I've drawn. I want to name the electronic geometry. That tells me the backbone shape. I have 4 groups around there. So that is, what is it? I'll count to 3. 1, 2, 3. Yes, tetrahedral. And then the molecular geometry, I need to say based on how many atoms there are. So this one is that diagram where I have 4 electron groups, and it's the subset of that where I have 2 atoms there. And so my molecular geometry here would be referred to as bent. If I cared about the angles, it's going to be roughly the 109 degrees that we see in the tetrahedral angle. Okay, and this would be the similar structure to water, H2O. Okay. So that's our first one. There's a final question about polarity. I'm not sure I want to totally get into that, but for something to be polar, we need an arrangement where a dipole, that is a distribution of charge, is not symmetric. So if I had something like carbon dioxide is a great example, I've got electron-rich environments at both ends of the molecule, and the center is positive, and so the negative charge that's sort of pointing one direction cancels the negative charge going the other. So CO2 would be nonpolar, something like this, because if we were to draw this out more accurately, if you will, whatever's going on with this fluorine-oxygen bond does not cancel with the other fluorine-oxygen bond. They're going to add to each other in one of the directions and cancel in the opposite, or in the perpendicular direction. So this guy would be polar. And again, your rule is if a molecule is totally symmetric, it's probably not going to be polar. If the symmetry is broken by these lone pairs of electrons sticking out somewhere, it probably is polar. Okay, there's one example. And one more example, let's look at the nitrate ion. So nitrate is going to have the nitrogen, oxygen, 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 and a negative charge. Nitrogen's 5 electrons, oxygens are 6, and that negative charge gives us one more, so we have 24 electrons. If I want to draw a skeletal structure, move this way this time, put the nitrogen in the middle. I don't really show the negative charge until I'm done, and I do that with square brackets, and I put a negative sign after, but I'll save that for a second. All right, so back to the way we did the last one. I have 24 electrons. I have 6 of them used up bonding, so I have 18 electrons left to spread around the atom. Doesn't matter where I start. There's 2, 4, 6, 8, 10, 12, 14, 16, 18. At this point, I'm showing 24 electrons there. The problem is that this oxygen, as drawn, has 2, 4, 6 electrons. Everybody else as drawn has 8. Okay, so this oxygen doesn't have enough electrons. The octet is not satisfied. So what has to happen is we share more electrons. In a way we can do this, I could take this pair and put them over here, but that would mean this guy doesn't have enough, so that doesn't work. But typically I can take a lone pair and share them. So if I take this pair and share them, then I haven't taken them from this nitrogen. Nitrogen still has them, but now this oxygen does as well. So go ahead and count these up. If we look at this, I see 2, 4, 6, 8. That oxygen has 8. If I look at this nitrogen, 2, 4, 6, 8, it also has 8. Okay, I have shown 4 double bonds, but it's not 4 pairs, it's 3 groups. So this right here gets too scribbled. That's a group. Even though it has 4 electrons, that's a group, and that's a group. So in this case, I have 3 groups of electrons, which means my electron geometry, count to 3, answer. It's going to be trigonal planar. And the molecular geometry, well, there's no lone pairs around that central atom. That's really what dictates the shape. So since there's no lone pairs there, there's the 3 atoms around, and so the molecular geometry is also that trigonal planar. Okay, so if I wanted to try to draw this guy a little bit artistically, I would just pick one of the oxygen bonds to have a double bond. I would kind of try to show that the bond angle there is about 120 degrees, and then to show that the number of electrons doesn't really match the atoms, namely that it's an anion, I do the square brackets and I put a little negative sign outside of that. All right, so again, there's 2 examples we've just done, nitrate and what did we do first? The oxygen difluoride. Did a little bit of electron sharing, and that's what we do. And I just want to add too, that a lot of this pushing electrons around, some people might just see it and do it instantly, other people struggle a little, and it's totally okay to do it as trial and error and see, oh, I need more electrons, I can't get more electrons, so I share them. And again, sometimes it takes a couple of tries to not mess the molecule up. But ultimately what you want to do is when you have a drawing is go through and make sure you have the right number of electrons and that each of the atoms has the octet rule satisfied. With the exception of hydrogen, it only gets 2 electrons, but everybody else gets 8. Okay, that's it.